Hello, this is the lab port for the first lab of constant velocity by me, Edwin Hernandez. Uh, we'll be using Newton's second law to find the constant velocity of a ball rolling on the table, and we will be using that video and its data to create a computer model in GlowScript IDE. The formulas that we'll be using will be Newton's second law and the position update formula. The formula for Newton's second law states that the final velocity equals the initial velocity plus the net forces over the mass of the object times the change in time, which is denoted as delta t. Velocity, which is denoted as v, is constant when the net forces, which is denoted as f net, is zero, which means that the final velocity will equal the initial velocity. We'll use this velocity and we'll be plugging in that velocity to using our position update formula, which means that the final position equals the initial position plus the plus velocity times the change in time, which is delta t, to update the position of our object in our GlowScript code. Some of the main assumptions of the for the models, for the computer models, will be that the mass of the object of the video, which means it's uh, about 1 gram. I had to assume it because I didn't know like the exact mass of the ball. That it was going in a straight line. It was kind of iffy on that one because it was slightly curving, and that the air resistance and the friction was negligible. So in the tracker model, we can see that in this model right here, in this graph that I put here from Microsoft Excel, that it's and going in a constant line in a positive direction for each increment of time s in seconds. So here's the video, and you can see that I started in the positive x direction instead of the negative x direction, and you can see it's increasing. It's a constant increase of space. This is my first GlowScript model. This is using the first and second data points to find the velocity, and the first and second data points are the 00, the time of 00 to 0.033, and these are the two x axes, two x points, and this is what I use to create this first GlowScript model, and this is the code for this one. And as you can see, this is the velocity that I created, 16.350 as my velocity. And if I run this program, you can see that it goes up to about 10.03522. But compared to the tracker, around this time, it was at 13.11. So there's a large discrepancy between these two models, and that's why I created a second model in this thing, this lab, which is this one, which I use the first and last model to point the final velocity, to find the final velocity, in which in my GlowScript, it came out as 20.697, and if I run this, it gets pretty close, but with a slight discrepancy of about 0.01 uh, of a difference, or 0.02 of 0.02 centimeters of difference of the discrepancy compared to the about 2 centimeters of difference between the first model and the second model and the tracker model. So the differences between these two is that, as you can see, this is the second computer model, and you can see that there isn't that much discrepancy, even if this one right here in the middle is slightly more, there's a slightly more discrepancy. It isn't compared to the first check and glow script, which is there's a large discrepancy of about 2 centimeters. close to about 2 centimeters of discrepancy between the computer model and the tracker model. So what does all this mean? This means that there's a couple of my assumptions were wrong or were not that accurate, and if I flip the axes instead of my positive, as I had it here, my tracker model had this on the positive x-axis. If I flipped it on the on the negative x-axis, if I moved my origin to where to where this 19th data point is, everything would just be flipped around, and I'll be the graph, instead of going up for every increase in time, there'll be an increase of x. It would have been flipped so that for every increase in time, there will be a decrease of x. And so, like, the some of my observations that I've seen of the net force is that there would have been a a couple of the net forces. One of the net forces that I put into it was the push. As you can see, when it was going around, it's moving at a constant pace, and that's my push. The one that it's trying to pull back at the ball, is friction and air resistance. So those two combined actually cancel each other out and made it into a F net equals 0 situation, which means it's a constant velocity. So some of my assumptions, as I said in the beginning, they were slightly off. The mass, I wasn't able to weigh the ball that I used in the video to find the correct mass. I assumed it was about 1 to 2 grams. So that's why in the code and in tracker, as you can see, I have 1 point e to the negative third kilograms, and in my glow scripts, you can see that my ball.m, the system mass is 0.001, which is kilograms in that, and it's the same here in my second code. And another one that said it was going in a straight line, isn't that true? Because like when I was editing the video, like the ball was curving towards the camera, and also one of the another assumption that I forgot to add was my camera quality. As you can tell, it was slightly blurry, so I had to estimate the center of mass of the ball. So if I would have done this experiment again, I would have a better camera quality and know the mass of the ball, and actually try to throw it in a straight line instead of a slightly curved line. And that's the end. Thank you for looking at my video.